to be aware of. I brought in one more, but I can't see where it is right now. Yeah, here it is. I got it. All right, let's get this set up from the current slide, and we'll go as soon as I finish the announcement. We're right in the middle of Cougar Connection Week. That's where Matthew and Dimitri are now. They're helping with the, what do they call it, Get On Board volunteer fair down around the library. And wow, there were a bunch of tables down there, so looked like it was going pretty well. And what they changed for this time, and I didn't hear about it this morning, was they had food today. So
some nasty food.
Yeah.
Good. Well, I almost got some twisted taste buds because I don't eat outside food. They had flies on it from these bootlegs.
All right. So coming up tomorrow on this campus is an HIV awareness seminar, and that's in the, if I'm reading this right, is A105, which I believe is the Space Center. I didn't know that was that big a room, so I'm a little surprised it's in there, but that's where it's listed. That's from 1 to 2 o'clock tomorrow. On the Birmingham campus, it's Serve Day, and the time for that is 3 o'clock. They don't specify what that is, okay? And before we meet again on Thursday, on the Birmingham campus, the student organization induction ceremony, and I'll read you that in just a few minutes. That's going to be at 1 o'clock in the afternoon, and in the evening, a pool party in the Arthur Shores building, which is the gym, and that will be from 4 to 6. So that's what's coming up for the rest of this week. So as I just said, come witness the installation of your student government. There's one right here. Student Government Association officers, the Lawson State ambassadors, as well as the induction of members of Phi Theta Kappa Honor Society and Kappa Beta Delta Honor Society for Business. The guest speaker is Galvin Billups, Executive Director in the Mayor's Office, Division of Youth Services, City of Birmingham. That will be Thursday, the 20th, that's the day after tomorrow, 1 o'clock in the afternoon, A.G. Gaston Auditorium on the Birmingham East Campus. Okay? Anything else to say about that?
I just walked in. I didn't know what you was talking about.
That's the SGA installation.
Yeah.
Student Government Association.
Yeah, you got one other officer in this campus. That's Dimitri, and more than likely we won't be here on Thursday, probably for the first half because of the induction.
Right. Okay.
Yeah.
So that's coming up Thursday. Now, are any of you at the point where you may be close to graduating? Yes. Okay. Have you applied yet? Okay. Yeah. If you're graduating this term, this is the time to apply. And it says the deadline to apply for fall term graduation is Thursday, the 20th. Okay? So get it done soon. Soon and very soon. Okay? So that's coming up.
And Halloween coming up, so if y'all throwing a party, the speakers, they you know, that's my only thing. Like, who cares about a Thanksgiving? I don't want to see it. So if y'all throwing a party, just hit me up on Snap. I'm show out, and you know, find myself over there on Bush, passed out.
All right. There is a new procedure for applying to graduate, and there's posters around on the thing. This one, I asked them to print, but it printed it this way rather than that way, so it's a little bit cut off here. 3-step process. You first do a degree audit. I believe that is you get your degree plan, see what you've done, see what you still need to do. Take that to your advisor, see the advisor, and the advisor will help you figure out what you need to do, and then you apply online through the website. So please try to get moving on that soon, because like I said, Thursday is the deadline for this term. But this is the perfect time to apply if you're going to graduate in spring term. because if you apply now, you get all that done before you have to register for spring term. So if you do have any courses you're missing, you can get those on the schedule right now, and as soon as we get the spring schedule out, you can get on that, and you can be in exactly what you need to finish out.
What do you recommend? This is good.
Okay, a little bit loud.
Let me get to Q&A.
Say that one more time. Okay. That's a good question. A lot of people have it. If I understand the question right, do I recommend that you're going to get your 2-year degree first and then transfer, or transfer when you just seem like you're ready to go? The one advantage of getting the degree first is now you have a degree in hand. So if something did happen in the next 2 years that you did have to start work, you already have an associate's degree. Don't have a bachelor's yet, but at least you have some degree, and that may start you a little bit higher than if you just transferred with the same number of credits, or awfully close to the same number of credits, but with no degree in hand, and then something comes up in the next few years and you don't get to finish your bachelor's, you basically are a high school graduate. Okay, so there is an advantage to go there. And what?
It's cheaper.
It's cheaper. Yeah, well, it's cheaper to take as many courses here as you can before you transfer, if they'll transfer them, because, yeah, you're absolutely right. We're less expensive. I like to say cheap. Okay, less expensive. No, I say cheap all the time. We're less expensive, but also you typically have smaller class sizes and usually have more one-on-one interaction with the instructors. In a 4-year school, I mean, it can be.
Yeah, like UAS, math classes that have like 200, 300 people in them.
Exactly. And a physics or physical science class, I was in classes of 200 in those too. And you don't get any one-on-one interaction with the instructor at all. You get a little bit maybe with a grad student who's your lab TA or something like that, but boy, not. Now, the one other thing, I hate to say it this way, but it's sort of true. Here, most of our instructors, English is their first language. And a lot of times at the 4-year schools, especially for lower level classes, you may not be so lucky, you know. And not that they aren't good teachers, they probably are, but understanding them might be a little tough, especially if it's a subject you don't feel really comfortable with. So there are some advantages, several advantages to the 2-year system. We're here basically to teach. A lot of times the 4-year professors are there to do research and they just have to teach. You know, so it's a little different attitude. Okay. But not that you don't get a good education, you do. Okay. Now, 2 other things. I think these are sort of centered on the Birmingham campus, but we always have needs on this campus as well. And if you do both campuses, then you'd be suited for this. The Office of Student Services, is seeking students who are interested in becoming note takers. I had a student in this class several years ago who I think had cerebral palsy, and he could not take notes. I mean, he didn't have enough coordination in his hand to do that. He had a note taker in class, and there were a few days his note taker didn't show up, and then another student would try to help him, and, you know, they do all they could. So it really is a need, and they must need some at the Birmingham campus, because this is interested students should contact Ms. Janine Jones, Student Service Specialist, and she's usually on the Birmingham campus.
Is that like a volunteer thing?
No, they pay you.
Oh.
They pay you. That's the deal. Student disability services, that kind of stuff, pays the note taker to do that. And you can check with Dr. Renee Herndon on this campus. She's here, and she will know if we have a need on this campus. She'll also know about the other campus, because she's in charge of it all. Now, in addition to that, the Space Center, I've already mentioned it once today, on our Space Center, I think it's down in room A105, but this came from the Birmingham campus. The Space Center is looking to hire peer tutors in the areas of math, English, biology, computer science, and Spanish. So if any of those are one of your strengths, check with them. Now, they say here to check with Miss Leslie Harper, who is on the Birmingham campus, but there is a guy downstairs, and I can't think of his name right now, really nice guy who runs our Space Center, and I'm sure he would let you know if he needs any tutors as well. So that's another good opportunity, and they pay you. Okay, let's see. Dante just came in, and just a little bit ago, Justin came in. And we're still missing Dimitri, Darren, and David, the 3Ds. Okay. All right, let's go on and turn on the projector and set up for what we're going to do today. All right, now, let's just talk about where we are and what we're doing, where we'll go from here. We are in chapter 19, and we have at least now less than 2 hours. We probably will be able to finish the chapter today. I'm thinking we will.
Do you have a test today?
Yes, we do. Okay. And that's just what I was going to say. If we finish chapter 19 in the first 2 hours, in other words, by 3:15, then we'll have the lab for chapter 19. Now, it's not special to 19. It covers stuff we've been covering for ever since we've been in the earth science part of this. Okay? It's on latitude and longitude. I brought up 3 atlases here that we'll be using in it. So that's going to be 2 hours from 3:15 to 5:15. At 5:15, or if you finish the lab sooner, you can start your test on chapter 18, okay? And I've got that ready too, okay? So test on 18, last 30 minutes. The lab for 19, probably the 2 hours before that, if we finish 19, which I think we probably will. All right, and by the way, the question was already raised. The field trip is 1 week from today, next Tuesday, the 25th. Just 3 Christmas shopping months till Christmas, okay? So we will be having the field trip then. And I had carried the stuff over to make arrangements on Friday. My boss wasn't in. I had to basically run the thing. I had to come up with second mini-term classes. I know they're going to cancel as soon as nobody shows up in them, but I had to find rooms. It's really not an easy thing. And, registry students, advising students, and he never showed up. He was at Huffman High School for an event for the dual enrollment, so he didn't make it back to campus at all. So I didn't get the approvals done, but I'll have this Friday also to get that done. All right. Any questions then before we get going today? Okay.
Can we just go on like a voluntary field trip, right quick? Like we could go to McDonald's or like the park. Cause I did my hair, and I thought that we was going on the field trip on today, and I wasted some good jam.
Okay. Now I didn't understand most of what you just said.
Never mind.
Okay, I thought that was pretty worth it. Okay. All right. We're talking this time about building the Earth's surface. That's what this chapter is. And we talked about the stresses, which are the forces that the surface feels, and the strains, which are the results of that, what comes out of that. One of those strains is the act of folding. Okay? What folds are bends in the layered bedrock. Now, as soon as you see layered bedrock, it should pop into your brain. We're basically talking about sedimentary deposits, because those are the things sedimented in layers. And because you can see the layers, the stratification, then when they have the folds or the dips or the other things, you can see those. Other things may go through folding too, but you can't, the evidence is not as clear. So we're talking mostly about sedimentary rock, the layered bedrock. The folds are the results of the stress that produce plastic strain. Now, what do we mean by plastic? The surface is bent, but not broken. Okay? Bent, not rebounded. It's permanently bent. And that's what we mean by the plastic strain. That's what folding is. Now, generally caused by widespread horizontal stress. I think we talked about, we did talk about this slide last time. I think we advanced on it. This, I think, is Grand Canyon or some of those areas like that. Look at the layered bedrock there. Everything is horizontal, okay? So there was no folding obvious in any of this structure. That's just erosion. We'll talk about that next time. However, here you can see there's an arch, there's a syncline. Anticline, syncline. There must have been at some time a pretty enormous stress, but it was plastic strain because you have bends. You don't have breaks necessarily. Now there could be some breaks in it, but basically you have folded structures there. That's what we mean by folding. The odds are this happened way, way deep, because that's usually where the plastic strain comes from, where it's hotter and the material is somewhat plastic. You know, it is heated up and it folds rather than cracks. We'll talk about those next. Okay? Now, a bigger, obviously, series of folds. Okay? This would be what kind of structure?
Is it the underarch or the
This is arc.
So
And that's called the what?
It's the same arch.
Anticline. And this is the trough, and that's called the syncline. Okay? This is a result of folding. Now, it looks like there also was a fault, a crack here, but it happened afterwards. It was originally folded material. This looks like almost a pure fold here. Maybe a little bit of cracking right in the bottom part. But look at the size of that. These are vehicles, buses, you know, big SUVs and RVs and things like this. And look at the size of that. Okay? Folding. Bends in the layered bedrock. You can see the layers there. That's how we can tell. And these form the anticlines, synclines, also domes and basins. Now, I don't know if this part back here is classified a dome or not. It looks like it's just the top of the arch. I don't think that's classified as a dome. So, good deal. All right. Now, since some more just came in, just to remind you, we're going to go 2 hours now. If we finish the chapter in those 2 hours, we'll have a 2-hour lab. And on chapter, well, the lab is just a lab. But then the chapter 18 test will be the last 30 minutes today. And if you have formula and equation sheet, I encourage you to have those prepared. All right. Now, this is the result of your dome. This was a dome here. It looks like there's been a lot of erosion here. Now, this is just a picture. The youngest formation is that on top, and the oldest formation is on the bottom, because the dome has raised up the older part and cracked through the younger part. The younger part, because it's not as well formed, eroded away because of that cracking. We'll talk about that in the next chapter as well. That's a schematic of it. This is actually an aerial view of what was a dome. Okay? Much of the dome has eroded, but you can still tell there was rising up here, and then the oldest, hardest material did not erode, but everything else around it did. This is old layers down here, newer layers here. Much of the new stuff has eroded away. But that's still a dome there. And I can't remember, I want to say that may be at Sundance Mountain, but I don't think that's in our current text. It was in a previous text. Yeah. So, can't say for sure. But that was a dome, which we talked about in the middle here. Okay. The next type of structure you have is not a fold, but a fault. Okay? You still have relative movements, but this time you have a crack. Okay? In other words, maybe the material is more brittle, or it happened more quickly, whereas a fold could have been more slow, done at a slower rate. It could be this was nearer the surface where the material was colder and therefore would be more likely to break, whereas a fold might have been deeper where it was warmer, would contribute to a fold. There's also the issue, remember, of the pressure. If this was near the surface, there's nothing on top, so there could easily be a sudden crack. When you're down way deep, there's pressure above and below, and that might be more conducive to a fold. This is a fault. Now, before we go too far on it, the very first paragraph here under faulting on page 485, they have another word that they don't show on the slide set well. But it says rock layers do not always respond to stress by folding, like we were looking at before. Rocks near the surface are cooler, under less pressure, so they tend to be more brittle. So that's going to be indicative of a fault rather than a fold. A sudden stress on these rocks, again there's a time issue, may result in a rupture point, resulting in a cracking and breaking of the rock structure. So that's why they mentioned the crack there. Now, if there is a breaking of rock without relative displacement on either side of the break, the crack is called a joint. Okay? Not the vernacular joint, but that's called the joint. If there is movement on either side, it's called the fault. Okay? So if there is a break but no relative movement, that's called the joint, and we'll see some pictures in the text of joints. But if you have a crack but relative movement between the sides, then that's called the fault. Okay? And they mention here that basalt often develops the columnar jointing without relative movement. And I don't think we have a picture in the slide set of a joint that they do of faults. But if you look in your book, figure 19.8, the top of that page, you'll see two really great illustrations of these are columnar jointing forms at right angles to the surface as basalt cools. It cools and basically contracts, and that forms these vertical often, but you could have it horizontal as well, joint. No relative movement there, just the cracks. Okay? Just the cracks. As opposed to faults, and those cracks are called joints, the one I just showed you, as opposed to faults. Okay, let me do this one first. Okay, well, let's go on and get it. Now, we call two different things. When we do have relative movement, very seldom is the crack vertical. Most of the time, the crack is at some angle. Okay? And the lower side of that angle is always called the footwall. The upper side, and I say upper, above the crack is called the hanging wall. Now, the hanging wall may have not hung as well and subsided. Dimitri is here. All right. So now we're just missing Tiara, who we haven't seen in quite a while, Darren, and David. David is missed quite a bit too. All right. So we have the crack at some angle. Below the angle, below the crack is the footwall. Above the crack is the hanging wall. Sometimes the hanging wall slides down the crack. the fault. Sometimes it's pushed up, and we'll see pictures of that as well. What would you say this was up here? Hanging wall. Down here, foot wall. Which direction is the hanging wall gone? Down. Okay? You see this line here used to be adjacent to that. This line used to be adjacent to that. You can't see this one down here. Okay? But you can tell the hanging wall has slid down the foot wall. That's the fault. Now, if there had been a crack there, but no relative motion, that would be called a joint. You seldom have it with angles like that, but it could be. Okay. Now, the hanging wall is the mass of rock above the fault. The foot wall is the mass of rock below the fault. The fault plane is the surface between the foot wall and the hanging wall. Identified here by the crack, it probably goes way into the rock structure there. Okay? It was an entire structural event, not just a surface structure. Entire event. Okay. Now, there are some classes of faults. We didn't have that many classes of folds except domes and basins and anticlines and synclines. But on the faults, we have a little more rigorous, you might say, classification. So here is what we call a normal fault. What we just saw illustration. The hanging wall has moved down relative to the foot wall. Both of the illustrations you saw in the previous slide were normal faults. Now, here's the related features that sometimes happen. Sometimes, not always, but sometimes. Now, don't get too bent out of shape on these. These are very seldom used terms in my mind, but it can happen. The graben is the block surrounded by normal faults, drops down. Okay? This would be a normal fault. Okay? The foot wall's down here, the hanging wall's over here, but the hanging wall has slid down the fault plane. Okay? Now, they don't mention it here, but let me mention it now. Notice the stresses. What kind of stresses are these? Pulling apart. That has a name. They're tensional stresses. Okay? Tensional. The tension pulls them apart. And that's what creates the hanging wall falling down, the foot wall, because it's a tensional stress. Now, if you have a graben where you have two faults, both normal faults, and the foot wall sinks between, again, this will only happen with tensional forces. Now, the other forces would be compressional forces or shear forces. This is tensional forces, okay? Where the block in the middle, the hanging wall on both sides goes down relative to the foot walls on either side. The block surrounding the normal fault drops down, that's the graben. Okay? And again, this is just the term. The horst is when the block surrounded by normal faults is uplifted. Well, what basically is happening there, this is your foot wall with a hanging wall falling down on that side, a hanging wall falling on that side. That would create a horst. You know, it's a raised area. Here, the hanging wall falls down, and that's a graben. Again, these are not all that important, especially to us. I don't think we have many structures like this around. You'll see this more out, I say out west, where you have plateaus and other things like this, and wide open spaces, you'll see some of these features happening some more there. Now, again, it says surrounded by normal faults. If these were compressional and the foot wall and the hanging wall was raised, I don't know if that's not called a horst as well, but they only show this as tensional stresses and the raised footwall is the horse. The dropped hanging wall is the graben. Okay. Again, don't sweat yourself too much on that. Just a series of terms. But we're not through with the classifications. There's another type of fault called a reverse fault. This is caused by compressive stresses, where the forces are pushing the rock together, and now the hanging wall is forced to go up the footwall. See, with compressional stresses, that forces the hanging wall to go up. Okay? And the footwall just basically stays where it is. That is, the hanging wall is moved up relative to the footwall, the result of horizontal compressive stresses. Compressive stresses, okay. Now, there's another kind like that called the thrust fault. The difference between a reverse fault and a thrust fault is a low angle fault plane on the thrust fault. Pretty steep angle on the reverse fault, low angle here. Now, how does this really play out? Well, the way they show it, if it's a really low angle, the odds are you get very little evidence of this. Pretty direct evidence that's happening here. Very little here because these happen fairly slowly usually, and over time, the erosion and other things that are happening here sort of smooths this out so you can hardly tell it's happening. It's only if you look at a cut of it, you see there actually was a fault here. Just a surface trace of the fault, whereas here, a really big indicator of a fault. Okay? Now, faults provide information on the stresses producing the formation. If you have a reverse fault, you know it's got to be compressive pressures. Okay? If you have a thrust fault, it's a compressive stress, but it's also a very low angle, so you won't see as much evidence. If you have the grabens or horse, or the hanging wall going down the footwall, you know it's got to be a tensional stress. So you can tell what the stresses were that can result in the faults that you're looking at, just by the relative movement of that hanging wall relative to the footwall. Make sense? Okay. Now, in your text, there is an example, and they're mentioning a graben bounded on east and west by two normal faults. The fault plane of the west fault has a slope, and they give you that, and on the east fault is another slope. The sedimentary layers cut by the faults have been displaced 31 meters. How much extension has occurred? Well, we haven't even defined what we mean by extension. It's just playing around with numbers, which probably some geologist actually does this kind of stuff, and if you're interested in it, by all means, take a look at it. Okay. Now, there is a pretty neat picture in your book of a fault plane near Kingman, Arizona, and it's awfully close to a vertical line. So I don't know which you consider the footwall and which the hanging wall, because it's almost vertical. If there is a little tilt, then one on top would be the hanging wall. And looks like it could be, and this would looks like it probably is a reverse fault. It's just not all that obvious. Okay. Everybody got it? Now, another thing they mention here in the text, they don't mention as much in the on the slide set, is sometimes these fault planes and stuff will identify for you veins, maybe of marketable or mineable ores that you might find. there's no guarantee there any more obvious there, but those would sometimes be those really distinct changes of color. Sometimes that might be a valuable ore. All right, so that's your other faults. Let's move on to 19.3, which is earthquakes. Okay? Now, what is an earthquake? Well, sort of as its name indicates, it's a quaking, meaning a shaking, vibration, sometimes upheaval of the ground. Okay? Earthquakes are not the earth splitting in two and people falling in. That's Hollywood. That is not reality. Okay? It's a quaking, a shaking, vibration, generally caused by relative movement somewhere, usually very deep, and the vibrations bring themselves to the surface. Okay? Result from sudden release of energy from stress on rocks. Now, I've talked about this several times before, especially in your transform type boundaries, where one plate or one structure is trying to move past another, but they're never nice, smooth, well-oiled, seams. They're usually really jagged and rugged and things like this. So there's going to be rocks or things poking out there. They're going to get hung up on. But the forces are still there, but they just can't move. And the forces increase and increase until suddenly something gives way. Now, what could be the giving way? The rock could break. It could elastically rebound. Okay, anything like that could happen. Results from the sudden release of energy from the stress that's on the rock. Okay. Now, it could be if it was a tensional force. It could be it was being held together really well, but the tensional force keeps going, and suddenly there's a release this way, and then you have the hanging wall sliding down the footwall. That would be a sudden release. It could be a tensional force. A compressive force. It's very slow, very gradual, pushing together, but they can't really go anywhere until something gives way, and you have a sudden release, and that forces the hanging wall up the footwall, and that would create the vibrations. Now, these could be occurring really, really deep underground. They don't have to be at the surface. In fact, most of the time they're not. Okay, the vibrations are what we call the seismic waves. We talked about those in the last chapter, wasn't it? What were the three classifications of seismic waves? One stands for primary.
S waves.
P waves.
P waves.
And S waves, which are secondary. And then the surface wave. And Darren's here. Okay. So now we're only missing David and Tiara. So all the regulars are here. Okay, good. Appreciate it. So you have the primary waves, which are pressure waves. Yes, and they travel through solids and liquids. Your secondary waves are shear waves, and they travel only through solids. And then your third is your surface waves. That's the result of either of the other two waves. Once they reach the surface, then that's the movement that you find on the surface. Okay? Those are your seismic waves. That's what results from the vibrations when there's been that sudden release of energy. Most occur along fault planes. Okay? Now, some of those fault planes could be a subducting oceanic crust going underneath the continental crust. That certainly is a fault plane, a major fault plane right there. It could be things that are not that important, but still could be happening. Okay, when one side is displaced with respect to the other. Okay, that's usually where the earthquakes occur. Now, what causes them? One theory is the elastic rebound theory. That's what I was mentioning before. Did I turn off the other slide too soon? Did everybody get it? Was I? Huh? You got it. Okay. Okay. The elastic rebound theory. Two plates pressed tightly together. Friction restricts the motion. Stress builds until friction or rock rupture. So you see, I wouldn't call this elastic rebound if it's rock rupture. Okay. I would say that would be where one rock gives away but then bounces back. Okay, that's what I think of elastic rebound. There's including in this the actual breaking of the rock. Stress builds until the friction or the rock rupture strength is overcome. The friction strength is overcome or rock rupture strength is overcome. The stress rock snaps suddenly into a new position. That would be the rebound. It didn't actually break, but it snaps back into a new position. That would be one theory for the causes of quakes. Okay? One of the classic, especially for us living in the U.S., fault lines is the San Andreas fault. Okay? Now, you can almost imagine the North American plate here, the Pacific plate here, and actually on the San Andreas fault, it's a relative motion. I don't know which one's moving up and which is going down, but it's a transverse relationship. It's not compressive, it's not tensional, it's the shear. The fault line basically is the border of the U.S., of western U.S. and the Pacific Ocean. That's where the fault goes most of the time, including San Francisco Bay here, basically directly underneath the Golden Gate Bridge. I mean, you got a promontory here, a promontory there, right along the fault line. But then in Southern California, it moves a little ways inland and keeps moving inland. And this is where I pointed out, it looks like to me that just below here, they don't show this far enough, you have the, I think it's called Gulf of California. Very thin little finger of water that comes up here. This is the Baja Peninsula on this side, and the rest of Mexico on that side. And that seems to me, looking at this picture and looking at the globe, looks like it's right there. That Gulf of California, it makes you wonder if that wasn't the result of the fault line. I don't know, but it sure appears so. And back around the turn of 1900, they had a major earthquake in San Francisco, and a lot of, the 1849 was the 49ers, the big gold rush out of California. And that's when San Francisco went from a sleepy little town to being a fairly major city. And then inland from that, it drew a lot of people in fairly quickly. And San Francisco grew faster than it was planned for, so it wasn't the greatest of construction there. When they had an earthquake, and it was a major earthquake, but it really wasn't all that big. I mean, it destroyed everything. But by that time, they had natural gas, they had other things, and there were fires. It just destroyed the city. Okay. And then I've mentioned, since then, I don't remember which year it was, it seems like it was in the 60s, there was a World Series between the San Francisco Giants and the Oakland Athletics. Oakland's just on this side of San Francisco Bay, San Francisco's on the other side of San Francisco Bay, and they called it the Bay Bridge Series or something like that. The teams didn't have to go very far, back and forth. And they were playing, I'm pretty sure, in San Francisco one afternoon. Business going as usual, and there's a huge bridge right across here. It's called the Bay Bridge Tunnel. The reason the tunnel is tunnels through a tall island there called Yerba Buena Island. But it's a bridge through there, tunnels through the island, and then a bridge afterwards going to San Francisco. And the earthquake happened during the game, which had to be pretty scary. And but the worst part was on the Bay Bridge tunnel, the upper deck of the thing. One, it was upper deck, lower deck. One went one way, one went the other. It collapsed on the lower deck, which was filled with cars, and there were a lot of people killed on the spot, and a lot of others, if they weren't killed immediately, they really good chance they died. Because how do you get to rescue people with a bridge on top of you? I mean, that's just not good anyway around. And within just a few years of that one, then there was another quake down here near Los Angeles, not exactly in Los Angeles, but near, because the San Andreas Fault moves a little bit inland from that, but it was enough to shake Los Angeles, and there, exit ramps and things like this collapsed. Wasn't as major as here, but it still was. It messed up travel. And if you've ever traveled through Los Angeles, it's already messed up. It just messed it up really big time. So that's one of the two major faults in the country. The second one is mentioned just briefly in the book. It's not mentioned at all on the slide set. And that is one on page 488. It says, most earthquakes are explained by the movement of rock blocks along faults, but there are other causes. Earthquakes have occurred in the eastern U.S., and I mentioned one, minor one, happened in sort of central Virginia that did some major damage to the Washington Monument in D.C., the District of Columbia, but also shook as far south as Georgia, because it knocked the thing off the wall in our house. Didn't do any structural damage, but just knocked something off the wall. And my sister-in-law said knocked some things around in their house too. And without any apparent relationship to known faults at or near the surface. One of the largest, this is pretty incredible, one of the largest earthquakes on record in the United States occurred not in California, not in Alaska, none of the places you would expect it to, but in a region near New Madrid, I think is how they pronounce it. In Spain it's called Madrid. I think there they call it New Madrid, Missouri, in 1811. Okay? Now, if you remember what was going on in 1811, anyone recall? Especially the very next year? Okay, in 1811, we were a brand new country, right? We were, basically fought the War of Independence in 1776 through probably close to 80. We were under the Articles of Confederation as a government for, a number of years, and it didn't really pan out too well. It didn't work well. They were trying to fix it, and they decided to write a whole new constitution. And that finally got ratified and stuff. And the first election, I think, of George Washington was right around 1799, 1800, somewhere right in that time frame. And so we were a brand new country.
Yeah, Washington died in 1799.
What's that?
Washington died in 1799, and D.C. was pretty much established a year later, before the end of the Adams presidency.
Okay, so so maybe he had already served his time.
Yeah, he was out of president for 2 years before he quoted.
Yeah, okay. So he was a bit earlier, probably 1792 or something like that.
1797, he was reelected in 1792.
Right, okay. So that was his time. So 1811, okay. In 1776, we had fought against the British, won our independence. What happened in 1812?
Wow.
The War of 1812. All right, cleverly disguised. Yeah, and again, it was against the British. It came close to being against the French because both countries were saying, "Hey, this little pipsqueak nation coming up over here, they can't defend themselves. They don't really have a good navy, and they were just stopping our ships at sea and conscripting sailors, to fight, because England and France were always fighting each other. I mean, just almost continuously. They had one time something called the 100 Years' War. I mean, they were just always at battle with each other. And they would just stop and pull U.S. sailors off the ships and recruit them to be in their navies. And we finally said, enough of this, and we went to war against the British and talked the French into helping us. And actually, we did a few other things there, too, like Thomas Jefferson bought the Louisiana Purchase from France so that they could fund their war, so all these things were happening. So that was happening, and in 1811, this earthquake had occurred. Now, the reason I brought that up is it was just a few years later, I think 1814, when the War of 1812 was winding down. Andrew Jackson came down the Mississippi and basically routed the British from the port of New Orleans. And, the whole song was from the Battle of 1812. That came up, fired one round, and the British kept coming, that kind of stuff. But just a few years before this, he wouldn't have been able to do that. In 1811, in that earthquake, it was so major, they said the Mississippi River, and if you've ever seen the Mississippi River, it is one big body of water, okay? Wide, deep, one big. It flowed north for a day or two, and that earthquake occurred. That is unbelievable. I cannot imagine, but that happened, New Madrid, and so there is a fault there. The quake toppled chimneys 400 miles away in Ohio, was felt from the Rocky Mountains to the Atlantic coast, from Canada to the Gulf of Mexico. So that's the other fault line, the New Madrid fault zone, theorized to represent a failed rift that is being reactivated by compressional stress from east and west. Because these stresses are going on not just at fault lines in the middle of plates. They still are feeling the pressures, and it just happened that it happened then. Okay. Can you imagine if that were to happen today? You have a huge number of really big cities all up and down the Mississippi River, from Missouri down to New Orleans. There's several there, Vicksburg and some of the others. Then you have Memphis, Tennessee. Then you have St. Louis, Missouri. You have a bunch of large population areas all up and down the river. And if that were to happen today, that would be catastrophic. Okay, so I don't know. These things usually do repeat themselves, but hopefully that one will not. Okay. Again, read the book. You've got to read the book. It has so much more information than the slideshow can possibly give. All right, now here is one of the most incredible pictures I've seen. Now the illustration here, I think, is sort of wacky. You have these, this is called shear stress, okay? One plate is moving one way, one's moving the other. And then they show some bending and then a break. Very seldom things don't happen like that. But look at this. This is real life. That really did happen. This is some great agricultural land in the Valley of California.
Is that a cornfield?
That I can't tell what kind of field it is. It could be corn, soybeans, something like that. But it's just recently been planted, it appears. And this is where one of those quakes occurred. I'm guessing the one down near Los Angeles. I'm not sure though. And look at that. These rows were straight before. And look. It's not a huge, you don't see this kind of breakage. You don't see it. That's manufactured. That's probably 6 to 8 inches is all of a shift there. But that is pretty major. I mean, if you've ever planted or plowed a field before, you're going to have a lot of trouble right there because there's no way you can keep from killing something either on this side or that side because the fault line is right down the field. Okay? Pretty direct evidence there was plate movement going on there. That's a fault, not a joint, a fault. There was relative motion. All right. Any questions? Now, other ways we classify by location or intensity of earthquakes. So let's get a few bits
Can a
of.
volcano eruption cause a little earthquake? No.
Say this again.
Can a volcano eruption influence a small minor quake or a little tension in the little?
Okay. I would sort of say it's the other way around. I would say there probably was an earthquake that created the cracks, then the magma came up. So I would say the earthquake probably influenced the volcano, probably more likely than volcano influencing the earthquake. But it's a good thought. You know, they go hand in glove sometimes. Now, here's where some terminology. The actual location of the break, the thing that happened that created the vibrations, that's called the focus of the quake, where it really occurred. This is usually pretty far down beneath the surface of the earth. And we'll talk about these, the classification a little bit later. Now, what you always hear them talk about is not the focus, but the epicenter of the quake. The epicenter of the quake. You would think that's where the quake occurred. No, that is the location on the Earth's surface that's directly above the focus. Okay? The focus could have been way, way deep. Now remember, these fault planes are often at angles. And if it's way, way deep, the earthquake could have been down there on the fault plane, but above that on the surface, there's no obvious fault plane in sight. It may not show itself until way over here, miles away. Okay? But that's the epicenter, the location on the Earth's surface directly above the focus. Because that's where the waves will come first, because it's the shortest path to the surface. Now, a seismograph, size means the vibrations and stuff. The graph is the drawing of this. So the seismograph is the thing that registers and measures and indicates the strength of the earthquake. It's the instrument used to detect and measure earthquakes. And we'll talk about how that measurement happens a little bit later. So here's the three types of waves. We've talked about them before. We have the primary waves, longitudinal, the P waves, pressure wave. What else do we know about it? We know that it travels through solids and liquids, but there was one other feature between P and S waves. It's why they call it primary. It's faster. It travels faster than the shear wave, the S wave. So it arrives first. Always arrives first. It travels faster. The longitudinal waves, the pressure waves, travel faster. The secondary wave, or shear wave, or was there another one? It seems like there was another. But the transverse waves, these travel just a little bit slower than the primary waves. They happen at the same time, but the P waves travel faster. Okay? And then the surface waves are when either of these waves reach the surface. These are coming through the Earth. And when they reach the surface, they produce then the surface waves that go out like this. Okay? Up and down waves. They will be measured on the seismograph as well. They actually look like the biggest waves because they're on the surface. They're right there. But the P and the S waves really are the stronger waves, but they're coming from way, way deep in the Earth, so they don't create as much of a shake on the instrument.
You know where I want to see, but it would never happen because you can't. I want to see how the core of the Earth looks in person, but you can't.
No, you can't. Okay, we will have a awaken your memory. Okay, you'd be burned to a crisp. Okay, yeah. The literal thing is you wouldn't live to tell about it. So, yeah. All right. enough of that. Okay. Here is an illustration of what they're showing here. The earthquake actually occurs way down deep, and where it occurs, that's the focus. And from there, waves go in all directions, 360, all the way around, all these directions. Directly above that, and you see, here's the illustration here, here's the fault plane, and you can see the fault plane up here, but the epicenter is not on the fault plane. Because of the angle there, the epicenter may be miles and miles inland, but the focus is on the fault, okay, but way deep in the fault, and the epicenter is this point directly above that. And from there, the surface waves move out in these directions. These are primary and secondary waves moving out this way. The surface waves move that way. Okay? Kind of makes sense? Okay. Now, here is an illustration of the seismograph. Okay? The main part is firmly established in the bedrock of the earth. I mean, it's part of that. And then it has this swiveling pin here, and with a heavy weight here, kind of like if any of you are familiar with flywheels on a motor of some nature that keep it moving relatively steadily, that's sort of like this. It's a big, heavy mass here, and it's not going to move unless something pretty major does, and when it does, you record it. This is a wire that holds it swivel down here, and most of the time, it's just wasted paper. The paper is turning, and it's just little vibrations, but just normal seepage. When an earthquake strikes, that first P wave that comes in, we'll see a picture a little bit later. And there'll be a time it'll die down, and then you'll see another one. That would be the S waves coming in. And then it dies down a little bit, and then you get the big ones. Those are the surface waves. It's finally, the surface waves are being recorded. Okay? So that's what your seismograph is. The ground movement is this way, making the pin goes back and forth like this. Okay? And the system of doing this, the international agreements that are in place that do this, all the countries in the world have agreed to do this. They maintain these things. They report. It all works together really, really well. One of the best successes internationally. Science tends to do better than politics. Okay, politics, no one gets along. Scientists tend to get along a little bit better. Okay, so what do we know? The seismic data tell us a lot of stuff. And as we already said, why we call them primary as opposed to secondary? The primary waves travel faster than the secondary waves. The pressure waves travel faster than the shear waves. All the different names you can do. Okay? The difference in the arrival times, though, between those waves correlates to how far you are from the earthquake. Because think of this. What if you were settled in one place and someone was leaving you traveling at 70 miles an hour and someone left at the same time traveling at 60 miles per hour? For a while, they're within sight of each other, okay? But after a while, the 70 mile per hour, not moving a lot faster, I mean, only relative 10 miles an hour faster, but after a while, they're a little bit out of sight. So if you were to measure the distance between them here, there'd be very little difference. Over here, much bigger difference. Over there, much, much bigger difference. Same thing here. The P waves are traveling faster, so the difference in their arrival time, how long it is from the time the P wave gets to the S wave, tells you how far you are from the earthquake.
It's kind of similar to when the volcanoes erupt in a major way, when you see the explosion before you hear the sound. It's kind of similar to that.
Oh, okay. Okay, that's a pretty good illustration, and it's not just that. Lightning Same thing. You know, anything that you see and then hear later, that's because light travels at one speed, sound travels at a much slower speed. And the difference between that, and we use it in lightning all the time, the difference between those, if you say 1001, you see the lightning, 1001, that lightning struck about a mile from you, okay? If you're 1001, 1002, 1003, 1004, then you hear the thunder, that means it's 4 miles away. Same thing here. The time difference correlates to how far you are from the earthquake or from the lightning strike, okay? Very good illustration, okay? So, how do we know where the earthquake is? If we only had one seismograph, we could say, here's the seismograph, we got the difference in time, so we know the earthquake happened 300 miles from us. So that could be 300 miles in any direction. You wouldn't know it, but it was 300 miles away. But if you had a different station here, and they do, they have them scattered all over. So Chris had a station back there, and it was 200 miles from Chris. Then he could draw a 200-mile circle around him. I could do the 300-mile circle around me. Well, there we have 2 points. It's either there or there. You need at least 3, and that's why they say triangulation. Most of the time, you always need at least 3 receivers getting the signal. And we have them. We have enough seismographs all over the world that we can pinpoint the epicenter. That's on the surface. And then the issue of figuring out the focus, that's a little bit harder, but the epicenter, and to some extent the focus. So here's how that works, okay? Well, first, here are the time of the first arrival, that's a rather strange way to say it, of the P waves and the S waves. The P waves are always going to come first and later the S wave. The distance from the earthquake is in this direction. The closer those are together, the closer you are to the earthquake. The further they are apart, the more distance you are from the earthquake. And it keeps going this way, and that widens as you go. Okay? So the difference in the arrival time tells you how far you are from the earthquake. And your seismograph indicates that. You can see when that first P wave arrives, and you can see when the first S wave arrives. Okay? And here's then what I was describing before. If one seismic station measures the epicenter at 200 kilometers away, it's anywhere on that circle. This one measures it at 150 kilometers away. It's either here or there now, okay? But if you got a third station that's 100 kilometers away, it's got to be there. Can't be here because that would have measured you up. It has to be there. Now, is that only for seismographs and earthquakes? No. Any of you use GPS? I bet most of you do these days. Very few people don't use GPS these days. I still love maps. I'm a dinosaur. But, everybody does. To get that signal, you have to have 3 sources. Because you can't tell where you are unless you have 3 different satellites, basically, that you receive the signal from. If you only have 2, you're either here or there. You're either here or there, but you don't know which one. But when you have 3 or more, then you can really ping in on exactly where you are. So it works with satellites. It works with earthquakes. There's lots of things that we use it for. Thank goodness it's all computerized. We don't have to figure it out, or we'd be somewhere else by the time we finally figure out where we were. Okay, so that wouldn't be necessarily so good. All right, now how do we classify these earthquakes? Okay, these are classified basically on the depth of the focus. Now remember, the focus is where it actually occurred, somewhere way beneath the surface. But here's then the classification. The shallow focus earthquake, then in other words, the focus is not that far down. We're talking about 70 kilometers, which would be about 42 miles deep. That doesn't sound very shallow to me, okay? But that's what we classify a shallow focus earthquake, down to about 42 miles deep. About 85% of all earthquakes occur there. Why? Because near the surface, and that's not super near, 42 miles is not all that near, your rocks tend to be more brittle, therefore the more plate friction on the surface, so you have sudden breaks, okay, because of the brittleness of it. Then you have the intermediate focus earthquakes. These range from 42 miles down to about 180 miles down. That's intermediate, okay? Now you're into the upper part of the mantle. Here you're at the crust, pretty much at the crust. Now your upper part of the mantle is always hot, okay? So when you do have those intermediate focus earthquakes, they're really deep, but not the deepest. The deep focus earthquake are 300, now they've got an error here. I always have to look it up in the book.
Boundaries are 350 to 700 kilometers.
Yeah, that should be 350 here. Let me get my pen activated, dark blue. This should be a 50 here, 350 kilometers. Okay, so it matches. Okay, whoever did the slide sort of messed it up. Okay,
Yeah.
so this is from, like I said, 42 miles down to something on the order of about 200 miles down, okay? Something close to that. You're in the upper part of the mantle there. The deep focus earthquakes are from that, what did I say the second one was, 200 miles down, down to 420 miles. That's really, really deep. This is the lower part of the upper mantle. Why are you staying in the upper mantle? Why don't you go into the lower mantle? What's in between the lower mantle and the upper mantle? The asthenosphere. And you wouldn't have, this is where the plate movements are. Below that, there isn't any movement. So the plates, the seismic plates, the tectonic plates, they move above that. So this is all the lower part of the upper mantle. That's where the deep focus quakes are. There's only about 3% of all earthquakes are that deep. So what would that leave the intermediate? 3% for the deep focus, 85% for shallow focus. What would that leave the intermediate? Say again? Okay. About 12%. Because these add 88 from 100 is 12. About 12% are the intermediate focus earthquakes. Even though these cover a way bigger range of depth, there's just not that many. This is much deeper than that, wider range of depth, and still most of those are in pretty much the crust. Okay. Any questions? Still writing. Okay. There are some, I don't think the slide set is going to show the seismographic data. So here, I don't think this is actual stuff. I think this was taken from actual stuff. If you're really close, then the P waves hit, and they just barely begun to die down when the S waves come and hit, and then they sort of are dying down, and then the surface waves come. But there's a huge difference in them. That's at station A. At station B, the P waves, and then the S waves, and then the surface waves. But you see, station B is so much further away, surface waves aren't as majorly different from S waves as before. So that's basically how they come in. This time lag tells you how far you were at station A. This time lag tells you how far you were at station B. Surface waves, they don't enter the picture. You just see them bigger because they are affecting the surface more. Okay. Now they do give some pretty interesting examples here. I don't focus on these much. And frankly, what they want you to do with these is far more involved than what is really necessary. Which station is closer to the epicenter if one seismic station in Nevada receives a P wave at 4:30:15 a.m. and the S waves at 4:30:35 a.m., so 20 minutes later, while the different seismographic station in California receives the P wave at 4:29:59 and the S wave at 4:30:15. So that's 31 and 15. No, I'm sorry, 16 seconds later, whereas the one in Nevada receives it at 20 seconds later. Well, obviously, the one in California was closer. But you didn't even need to know that. All you had to do was look at the first, 4:30:15 as opposed to 4:29:59. One in California was closer. It got the signal first, but it doesn't tell you how far away it was until you know the difference in the P and S wave. So you know it was closer, and that's what the question is. Which station is closer? Well, obviously the one that gets the signal first. But what they're really meaning is how do you calculate the time? And then they give another example pretty similar to that. Okay. Can I move on now? All right, measuring earthquake strength. You know, we're going to see this now. Later we're going to see things about tornadoes and hurricanes. And, you know, these things are going to look a lot alike, okay, because these are all natural disasters, but there will be some differences. In the long past, they looked at effects of the earthquake. The structural damage to buildings, fires, landslides, displaced land, surface tsunamis, if you had a tidal wave. You know, they looked at the effects, okay? Well, I think I gave this example earlier, or maybe not. It was on the neighborhood of about 10 years ago. I don't remember exactly how long, but somewhere around 10 years ago, I think it was the day after Christmas, okay, the 26th of December, something like that, there was a earthquake in Haiti. And boy, did it destroy, and it was real near the center of...
This past December?
Second?
This past December?
No. This was, like I said, about 10 years ago. Not exactly 10, plus or minus from 10. There was a major earthquake near Haiti, and it was real close to Port-au-Prince, which is the capital city, largest population area. Oh, you talk about structural damage to buildings, fires, landslides, you know, everything was happening there. So that was, in the old days, that would have been classified a really, really major quake. Okay? Something like 2 or 3 months later, there was a quake down in Chile, you know, this city in the country in South America that is up and down the west coast of South America. And it was a major earthquake. But it really didn't do that much damage, partly because it was not as major a population center and not that many buildings real close to it. But it's still, guess what? It's a much more powerful quake than the one in Haiti. But see, Chile was used to having earthquakes. So their building code, they had all their buildings built very earthquake resistant. Spent a lot more money in the construction, made it happen. So their structural damage was minimal. Okay? Sure, it didn't happen real close to a big population center, but still did. Haiti had never really experienced that many earthquakes, but they're a very poor country, and they just put nothing into, if they had any building codes, no one enforced them. So they were concrete block structures, they were rickety structures, and boy, the devastation was enormous. Even though the earthquake was much more minor in Haiti than it was in Chile. Okay? Well, way back they had what they called the Mercalli scale. It sounds like an Italian guy. I don't know. That would be a good paper topic. Speaking of which, papers. Let's see. This class, I've gotten, I think, 5 in so far, which is better than most classes, but that means I still have close to 2/3 of the students who have not turned in a paper yet. And guess what, folks? We're basically past midterm, aren't we? Or awfully close to it. Yep, we're in our 5th week, and this is an 8-week term, so we are past midterm for a mini-term. So don't forget your papers. Okay. So the Mercalli scale was basically on relative intensity, whatever that means. How intense did it seem to be? And well, what it was is whether you felt it or not. Okay? So not felt would be a 1 on the Mercalli scale, and a 12 on the Mercalli scale was total destruction, visible ground waves. The surface waves are obvious there. Okay? Relative intensity. Not really the best measure. Okay? Now you'll see something like this in a few chapters when we do weather. You'll see one like it for tornadoes. You'll see one like it for hurricanes. Okay? Earthquake safety rules put out by National Oceanic and Atmospheric Administration. Anyone know the shortcut that what that's sometimes called? NOAA. NOAA. If you ever hear on the news or stuff like this, and NOAA says this, and NOAA says that, you say, who in the world is NOAA? Well, that's what it is. It's the National Oceanic and Atmospheric Administration. So during the shaking, you know, you can say don't panic, but guess what? Panic isn't going to do you any good. It's not going to stop the shaking. Just kind of go with the flow, okay? Try not to panic. If you're indoors, stay there unless the ceiling's falling in or something like that. Seek protection under tables, desks, doorways, someplace that's stronger. Not in the middle of a room. Stay away from glass. Max, move if we have an earthquake, okay? All right. Don't use matches, candles, or any open flames. If you've got any fire burning, put it out right away. If you're outside, get away from buildings. Don't go into a building. Don't go anywhere near power lines. They may be coming down. Stay in the open. Don't run through or near buildings. Okay? Because who knows what's going to happen to those buildings. There could be aftershocks. Now, I think I would also say, I don't like the idea of staying in the open. I'd rather be in a ditch or something like that rather than out in the open. But I don't know. I don't think it really matters. But, okay? Probably not under trees, though, because the trees could fall down. So, and if you're in a moving car, stop it. Get out of the car, but stay in it. The wheels, the suspension will actually help you, but don't park under a bridge. Okay? That's not the best place to park. Do it just like it says here, stay out in the okay? There's no advantage to getting underneath something because it could fall on. Now, after the shaking is over, sort of subsided, it says check but do not turn on utilities. If you smell gas, open windows, shut off the main valve, get out of Dodge. Okay, leave the building. Okay, report the leak to the utility. Don't re-enter the building until it's been checked out. If water mains are damaged, shut off the main valve. If electrical wiring is shorting, close the switch at the main meter box. Do all you can to stop the arcing, sparking, fire, and anything else. Okay? Get on your weather radio, television if you got power. you don't have power, if you have battery operated, do it. There are some radios out there that you can turn a crank and charge and keep them going for a while, for a long while. Okay? Stay off the telephone except to report those emergencies. Don't say, hey, what happened to your house? No. You can find that out later. Okay? Stay out of severely damaged buildings. They could collapse during aftershocks. And do not go sightseeing. Oh, hey, did you hear out in Pleasant Grove, they really had it bad. No, don't go looking for something else to happen. Get out of the way of emergency personnel, repair crews. Now, this thing about where is it? Well, I don't see it now. Yeah. Stay out of severely damaged buildings that could collapse in aftershocks. This isn't the same thing, but it's similar. When I was in college, I was on one of my midshipman cruises. Coming back, I think it was the summer between my freshman and sophomore years. And my family was supposed to meet me in Norfolk, Virginia, visit with my mom's family there, and we were just going to have a nice time driving back. I got to port, nobody in sight, okay? I had to wait till they set up some phone lines and stuff, and then I called my aunt, and she said, yeah, they haven't been able to get in touch with you because you're out at sea crossing the Atlantic. They can't come. And what had happened, my younger brother and my older brother had gotten into sort of a spat. My older brother was going on his midshipman cruise. He was 2 years older than me. And they were going to take him somewhere. My younger brother, Dan, didn't want to go because they had been fussing. So he arranged it to go and spend the night with a friend in town. So they did, in small town, Georgia. Not much happening. They were out riding around. They heard fire trucks. Oh, let's go see what's happening. So they went. And sure enough, there were some houses burning. And it was in a poor part of town, and they were not very good structures, and they were going up pretty quickly. Well, some families nearby were worried, so my brother and his friend, this really surprised me that they were altruistic, but they volunteered to help them move the furniture out. In case the house really started burning, they could save some of their stuff. So they were helping. That happened down the way. The firemen were trying to put out the fire. And they did come so far, and then this next house that they had been helping with, it was spared. So I think they had started either moving things back in or something, but this house had burned, and this house was spared. So Dan was walking between the houses, I think carrying stuff back inside or something, and one of the volunteer firemen, and I happen to know him, just decided to start spraying that hot chimney and watching the water hit the hot bricks and make steam, and he thought it was cool looking. So he just turned on the water and was doing that. Well, that knocked the chimney over onto my brother, who was walking between the building. He didn't know Dan was there. It was dark. And so Dan was buried under a pile of bricks. Some of them were quite hot, some of them the other side, and he came out of it. My parents were out of town. They were taking Mike to wherever it was to catch his flight. They weren't in town, and Dan was in misery, and they wouldn't do a thing for him in the emergency room until they had parental consent. And it was a mess. So, what's that?
Talk about a lawsuit.
Well, yeah.
I would ask so too.
Yeah. Well, everybody knew each other there, and we knew how dumb that guy was, and he couldn't afford anything anyway. So anyway, we all came out of it okay, except Dan. He had some pretty major third-degree burns on his legs. Fortunately, nothing that was permanent. Well, obviously disfiguring. He still has really bad scars on his legs, but most of the time he keeps his pants on, so you don't see that. On the beach, sometimes you'll see it. Okay. All right. So stay away from buildings, especially because it could be aftershocks, not someone spraying water on it, but same effect. Something could come tumbling down. Okay, so Mercalli scale, not the best scales. Here came an American, Charles Richter, I think from Caltech, out in California, where they are fairly interested in earthquakes. He came up with the scale based on the actual swings of the seismograph recordings. Okay? All this data are shared and sent to one another, so they record it, so they can estimate by how far that needle moves how strong the earthquake is. They used a logarithmic scale, and what you can do with a logarithmic scale that's based on exponents. Okay? So a 3 is not felt. Okay? A 9 is the largest measured so far. Basically, that means 10 to the 9th power of energy, as opposed to 10 to the 3rd power. This would be 1,000 joules, say, or something of energy. This would be, goodness gracious, so many trillion, or so hundreds of trillion, largest measured so far on the Richter scale. Now, a log scale enables you to take huge numbers that are really wide apart and put them on a scale that's much closer, like 3 to 9. Okay? So here's what we got on the Richter scale. 0 to 2 are the smallest detectable earthquakes that the seismographs can't even pick up. 0, nothing's happening, but up to 2, only seismograph, no one's feeling a thing, but you know something's happening. Okay? 2 to 3, detected and measured, but not generally felt by anybody still. Okay? 3 to 4, felt as a small earthquake, but no damage occurs. Okay? 4 to 5, minor earthquake, local damage. That's probably the one that happened in Virginia, what was it, about 6-8 years ago, that damaged the Washington Monument. 5 to 6, moderate earthquake with structural damage. You will see this. Now, they're giving the structural damage here, but you see a 3 to 4 in a really lousy area like Haiti that doesn't have good earthquake building. That could be a lot of damage there. 5 to 6, moderate earthquake with structural damage in a place like maybe San Francisco or Chile or somewhere like that. They may not have much damage because it's built according to earthquake codes. 6 to 7, though, you're getting into very strong earthquakes with destruction. Okay? 7 to 8, major earthquakes with extensive damage and destruction. 8 to 9, total destruction. I mean, nothing, no building codes are going to withstand that. It's just complete wipeout. Fortunately, we don't have that many of those. I'm just trying to think of the ones I've heard most recently. I think the latest was in Japan, on the northern island of Hokkaido, I think is the name of the island. They had one
this year?
Somewhere, yeah.
Yeah, it was recent.
Yeah, I think that was in the 6 or 7 range. It was pretty
What was
powerful.
what was the Richter magnitude on that Japan earthquake back in 11?
Yeah, that caused the tsunami and the nuclear meltdown?
Yeah.
I don't recall. I think it was pretty powerful. I would guess in one of these two ranges here, but it was so close to land. That's what
Somewhere between 6 and 8.
I'm guessing. I don't recall for sure, but most of the ones that you hear something about are up in those ranges. Could have been as low as 5 to 6, but I don't think so.
Yeah,
I think it would have to be.
yeah, you'd have to have like a powerful Richter magnitude to trigger that tsunami.
Yeah, I think so. Way back, not way back, but 10 to 15 years ago, there was one that hit off Indonesia and caused a lot of damage on the east side on Indonesia, but also on the west side in India and Sri Lanka. And I mean, some pretty major tsunami there too. That was a powerful quake. So sometimes the most powerful, the largest measure so far, I believe, was in Alaska. And it was really, really major, but fortunately it was not near any major population centers, so there wasn't that much structural damage, so Mercalli scale wouldn't have counted it very much, but it was a very powerful quake. But probably who suffered more from it were people in Hawaii, because the tidal wave was so major from that, it wiped out some of the north shore of Hawaii, and that was a long, long way away. So Hawaii probably felt more damage than Alaska did. I mean, rock damage was in Alaska, but, building damage and stuff like that was more in Hawaii. All right, now that slide there, I had forgotten it's here too. So I'm not going to read it again, but if you're going back over it, don't try to read that little one. Use this one. And they're both in the book somewhere. Let me see if I can find them. Yeah, top of page 492, earthquake safety, everything is right there as well. And the table 19.1 that we just had up there on the Richter scale, that's there at the bottom of page 492. There's a couple more examples there. Now here, they don't have it on the slide set, but let me read it to you because this is pretty important. Remember the log scale. They're exponents you're dealing with. So what that means, and I'll give you the example here, there's two things. The higher the magnitude of the earthquake as measured on the Richter scale, the greater, number one, the severity of ground shaking vibrations. That's what it's measured by, the seismographic vibrations. And number two, the energy released by the earthquake. Now they're related together, but they're not the same scale. An increase of 1 on the Richter scale means the amount of movement of the ground is increased by a factor of 10. Think an exponent. 1 on the Richter scale, that would be like going from 10 to the third, which would be 1,000, to 10 to the fourth, which would be 10,000. So it's a factor of 10 on the shaking. Amount of energy released is a factor of 30. So it's not just 10 times, it's 30 times the energy release for every point you go up. Okay? So it says, example 19.5, compare the energy released by an earthquake of magnitude 7.2, earthquake of 7.2 magnitude to an earthquake with a magnitude of 5.2. Well, the shaking would be a factor of 100. It says 2 on the scale, 100 times more shaking. Variation straight. And 30 times 30 is 900 times the energy. Okay? So that's what that solution is showing you. And then they say the amount of ground movement would be 100 times. Okay? That was example 19.6. All right. Everybody got it? All right. Whoa. They have a little blurb there on tsunami. Tsunami, that's the Japanese word for tidal wave. It gives some pretty interesting data here. A gently sloping sea floor and a funnel-shaped bay can force tsunamis to great heights as they break on the shore and are funneled into canyons and fjords. The current record height was established in 1958 when the tsunami reached 524 meters, that's 1,720 feet up, the Litua Bay in the Gulf of Alaska. Ooh. Waves of such height and great and long wavelength can be very destructive. That tidal wave that was created, that Indonesian earthquake, when it hit Madras, India, even though probably the tidal wave coming across the Pacific was not more than a meter or two high, I think the Indian Ocean, more than a meter or two high. Once it got close to the shoreline, it actually grew because now you got water going up and coming down. So, and again, the geometry of things made it actually grow. And it probably went several meters high and several meters on a gently sloping beach, completely swamped large areas of land. And it did. We had friends from India, from Madras, now called Chennai, who had relatives who were on the beach that day, and they didn't hear from them while they feared they had died during the tsunami. But later, once phone service was reestablished, because it wiped out phone towers, so no one could get through. All right, so now we're going to go to 19.4, which is origin of mountains. Okay, how are we doing on time?
It's 3:01.
3:01. So if we finish by 3:15, we're done. I don't think we're going to make it. Okay, so it looks like there might. Well, let's see. Okay, origin of mountains. What are mountains? Well, you've got a good probably concept of it. Elevated parts of the Earth's crust rising abruptly above the surrounding surface. Okay? You can have places that are way above sea level, but they're gradually going above sea level. Okay? Those are not classified as mountains. You can have areas that are really flat, and then suddenly something jumps up, that's a mountain. Even though it might not be as high as this other place was that gradually went up. That would be a mountain, this would not. Okay? For instance, the tallest mountain in the world, Mount Everest, in the Himalayas. However,
ain't Hawaii a little bigger only?
Okay, yeah, if you counted from the base of the mountain that you see, yeah, and there are even more taller than Hawaii. But yeah, I see your point there. But on the surface, okay. But Mount Kilimanjaro in Kenya, because it's really flat, low area, and then Mount Kilimanjaro, it's actually taller above the surrounding area than Mount Everest is. Because Mount Everest, the whole area is way up there, and then Everest is on top of that. So its elevation is greater, but the height above the surrounding areas is actually less than Kilimanjaro, even though it's way, way taller than Kilimanjaro. Total elevation. So it's the elevated parts of the earth crust rising abruptly above the surrounding surface. That's what makes a mountain. Now, I always, when I see this slide, I think of a really funny, but supposedly based on a true story. Do y'all know who Hugh Grant is? A British actor. He was in a lot of the, Sense and Sensibility or some of those things. But, and it's a bunch of movies. He's usually really funny. But he was in this one. He was pretty funny, but it was a more serious role. It was The Man Who Went Up a Hill and Came Down a Mountain was the name of the movie. And it was actually somewhere in Wales, I believe it was, a surveying crew that was going through and found out this one local mountain wasn't quite tall enough to be classified a mountain. And it just got all the people upset because that was their mountain, and now it's just going to be called a hill from now on. It's going to be on the maps as a hill, not a mountain. So what they did, they started carrying things up to the peak and building it up so it could get those few more feet and be classified a mountain. But it was a pretty interesting movie. But that's what it is. Okay? Now, how are mountains formed? Two ways, and then a third way. Two ways: folded mountains. The crust is folded and grew, or it faulted and grew. Okay? And then we also have volcanic activity. So, created by folding and faulting of the crust, with three basic origins: folding, faulting, and volcanic activity. Okay. Now, and as Zachary was mentioning, the faulting could be related to volcanic activity as well, but usually we classify them just as one or the other. The Appalachians are basically folded mountains, though some of them have faults too. I don't know if there's any volcanic activity there. whereas the Rocky Mountains are mostly faulted mountains, though there probably are some folds there too. I don't know if there's any volcanic activity in the Rockies themselves. I wouldn't be surprised if there's not some. But then further west in the Cascades, they're mostly volcanic, but you probably have some faulted, maybe a few folded mountains too. So it's not clearly one or the other always. Those are the basic origins. Okay? So let's look at the folded. And were y'all through with that? Did I move too soon? Okay. Let's look at the folded and faulted mountains. These are often your domed mountains. Begin as a broad arching fold, and then overlain with sedimentary rocks. That's where you see the folding. They weather away, leaving the more resistant granite peaks. Okay? But they were folded mountains. Like I said, most of the Appalachians are folded. If you look in your book, the picture on page 493, you can almost tell the folds. This is an aerial photograph of the Appalachians near the Virginia, Tennessee, Kentucky boundary area. Blue Ridge Mountains are in there. They're all part of the Appalachians. You can almost see the folds there. I mean, not exact, but you can. Now, they weather away. In fact, the Appalachians are weathering away. They are growing shorter every decade or so, because they're weathering away. There's no new forces pushing them upward. Okay? Those are the folded and occasionally faulted mountains act the same way. I think we're going to have a picture here. Yeah. This is your dome mountain. Okay? You have some sort of pressure underneath, and it just sort of rises. The surface erodes away, and you're left with a hardened bedrock, maybe granite there. Now, if I'm not mistaken, Stone Mountain in Georgia is obvious, I think, is a dome mountain. I don't know what forced it up there, but something forced it there, and it's one huge piece of granite. Okay? Now, it's not my favorite mountain in the world because of what's carved on it, but it's a really good example of what I think is a domed mountain. I mean, it's flat, a fairly flat area all around. Just this huge chunk of granite right there. Now, whether it's technically a mountain, I don't know, but everybody calls it Stone Mountain. Okay. All right. Everybody got this now? No, still writing. Okay. Anybody else? Okay. Now, nothing changed except the picture went away. So, those are the folded mountains. Now the fault block mountains. These rise really sharply along steeply inclined fault plains, and you can just sort of see there's no folds involved with them. They just are these sharp increases, elevations here, and you can almost see the fault plane. Okay? Weathering erodes the sharp edges away, but when they first happen, in fact, this is a pretty good thing. When you look at the mountains and you see the sharp peaks, good indication those are fault block mountains. If the tops are rounded, those are probably more folded mountains. Now, you can't always tell. The age of the mountain will contribute to those kinds of things too. And actually, we'll learn in a later chapter if they have a history of glacier movement in them, that could have made some sharp peaks, but they weren't originally peaked. They were glaciers cut out the sharp peaks. So you can't always tell with that, but most of the time, if they're really sharp, jagged-looking tops, they're usually faulted mountains, fault block mountains, where the rounded is usually folded mountains. Not always, but usually. Now, here's the illustration. These are the fault planes that we talked about before. These would be your, let's see, what is it? I think these are the Grabens, okay? And I don't think they classify those as forests, but they could be, okay? That's what happened right when the very sharp edges and things like this shortly after it was formed. But then over time, erosion has worn off the edges here, and when the erosion happened, it washed downhill, filled up the valleys, so they're not as deep as they were. So the mountains aren't as distinct as before. They're rounded. So this could have been a fault block mountain, rounded top, and we might say, oh, that looks like a folded mountain. No, it's a fault block mountain that eroded.
We got 4 more minutes.
4 more minutes. Okay. All right. Anyone need that any longer? Okay. Now let's look at volcanic mountains. And these are so interesting. And I'm almost tempted. Okay. Let's take a time out here and talk about what we want to do. If we continue, we only got a few pages more, and then we'll get started in the next chapter. Okay? Or, I don't usually do this. Usually I like to finish a chapter before we do the lab. But because the labs are not that chapter specific anymore, for instance, today's lab is on latitude and longitude, which we've talked about in lots of previous chapters, really haven't even mentioned in this chapter. Okay? So, we could stop at our allotted time, do the lab, but then come back next time and finish the chapter and get started on the next chapter.
Excuse me, but what about the test?
The test will be the last 30 minutes today, no matter what. If we continue and finish this chapter and start the next chapter, we'll still stop at 5:15 to have the test. However, if we stop here and do our lab, and then next time we'll pick up at this place, and then we'll probably go a long day that day. We won't finish enough for another lab. So it may be that since we have the test anyway, maybe we should keep going. What do you think?
I think we should do what you previously planned. 2 hours on the note-taking time, 2 hours on the lab, and 30 minutes on the test.
Okay. So we'll stop soon and do that. That means that next time on Thursday, we'll probably have a good long time, because we won't be a test, and the odds are we won't be ready for a lab either. Okay? So that means next time is going to be a good long day. Huh?
Yeah, we got 2 minutes left.
Okay. Well, we can do whatever we want to. So we want lab time now? Okay. We'll try to, and then, next Tuesday, we're going to be, most of our time spent traveling at Sanford, traveling back with just a little bit of class time. So we'll have a long lab time next week. Okay. All right. Well, then we'll start with volcanic mountains next time. And we will do the lab this time. Do y'all want to take a break? Since this is a natural place for one, try to keep it 5 minutes or less. And I don't think I'm going to need, I think will be important. Okay, what today's lab is covering is latitude and longitude. All right? You're reading this on page 339, well worth a read. It's been a week or so since we did this in class, so you'll probably need to review that. We're not going to be playing with soft clay. That's not what we're doing this time, so the materials don't quite apply, but the pictures they have they illustrate what is latitude and longitude. So please read and use the pictures to understand what's going on there with the latitude and longitude. The pictures are worth lots of words. Okay? Now, based on your reading then, you should be able to answer question 1 on page 342, question 2, and then for question 3, okay? According to a map or a globe or an atlas, right here, Alabama Atlas and Gazetteer, whatever that is, and I can help you find the pages, but I bet you most of you will live on pages 31 or 30 or 31. If you don't, I'll help you find the page you do live on. It says, so you go to this and find the location and come up with your approximate latitude and longitude where you live. Okay? So that will be here. I'll leave it on those pages, but you might be a few pages off from there. I'll help you find it if you don't live on one of those 2 pages. So that's number 33 on the bottom of 342. Top of 343, again, is explained back in your reading. Basically on page 339, the last full paragraph there tells you a little bit about that. You might find some other places too. Okay? Now, then I wouldn't do number 5 yet, but now we've got, that's only 5 points worth. You need to have up to 20 more points worth of material. So I would say on the back of your page, okay, or if you'd rather use clean paper or a new sheet, you can. What I'd like you to do is number 1 to 10. Use as much of the page as you can. Don't get too crowded. Number 1 through 10. Okay? And then what you do is come up to the front, and there are 8 cups here. You will pick 1 strip of paper out of each cup. I happen to be in the Africa cup right now. I pulled out a strip of paper. Yeah, that's a city in Africa. Okay? Write it down next to your number 1 or whatever. You can do any order you want to. You'll need 10 cities from those 8 cups. Well, how are you going to do that? 1 from each cup. Okay? The other 2 you choose from, you can pick a second city either out of the Africa Cup, the Asia Cup, or the Europe Cup. Okay? Pick a second city out of 2 of those 3 that I mentioned. Africa, Asia, or Europe. Okay? Pick a second city out of one of those and write those down. So you'll list 10 cities here. Okay? Now, one of these cups is an Alabama Cup. And from the Alabama Cup, you'll get your latitude and longitude out of this same gazetteer. One of those cups is a U.S. Cup, United States Cup. You'll get your latitude and longitude from this book. Okay? And all of the others, there are 3 atlases scattered around here. 1 there, 1 there, 1 here. And the other cities that you got from the other cups, you'll get from one of those 3 atlases. Now, if some of you have that something on your cell phone, you can get latitude and longitude, what you've got in the cities, you can do that, but I would say you'll get a little bit better understanding of it actually looking at the maps. But you can use whatever you want. Okay? And we got the atlases here. I'll be glad to help. Please don't make some assumptions that wind up with bad information. Now, let me tell you how you list latitude and longitude. And this is where I thought maybe I will write a little bit more on the slide here. Now, the rest of the slide has nothing to do with what I'm about to do. Volcanic mountains have nothing to do with it. But your latitude, let me get my pen back. Okay. Latitude is going to be generally 1 or 2 digits, degrees, 1 or 2 digits, minutes, and 1 or 2 digits seconds, just like we did when we were doing celestial things. Yes? What's that? What's that now? I'm going to write it right here. Okay. Okay. Your latitude, and this will be latitude, then it's always followed by a letter, either north or south. So you have degrees, minutes, seconds. Now, some of those that you get from these books, you're not going to get any seconds. And some of them, in fact, the U.S. map, you're not going to get seconds. Only the Alabama map will you get minutes and seconds. The U.S., you should be able to get degrees and minutes. But these others, degrees may be as close as you can get. And you may get any better than nearest degree or nearest 5 degrees. Okay? But get as good as you can. But you always follow the latitude with a north or a south. The longitude, on the other hand, is going to be 2 or 3 digits degrees, 2-digit minute, 2-digit seconds. So that's only for Alabama, always followed by either east or west. If you leave off the N or the S or the east or the west, I don't know where you're talking about. So I need to have at least degrees for Alabama, degrees, minutes, and seconds. For U.S., degrees and minutes. For all the others, probably just degrees, but you have to follow it with north and south for latitude, east and west for longitude. Okay. Now, what Ishmael, I think, was just asking is how I would suggest that you do. You've numbered 1, 2, 3, 4, 5, 6, blah, 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 blah. Okay? Then put the city here. You probably want to give the country as well. Okay? You might even give the continent if you want to. Okay? You've got room, you can write it if you want to. Then you give the latitude, then you give the longitude. So is that what you were asking for? Ishmael, is that the format you were talking about? So you've numbered 1 through 10, you pick out city. Now, here's what I recommend. Pick out the city, write it down, put it back in the cup. Otherwise, if you pick out all the cities, then you're going to put them back in the wrong cups. So pick out the city, write it down on your piece of paper, and put that city back in the right cup. Now, if you think you pull out a city that's not in that continent, ask me. I guarantee you there's some wrong, because these have been used and abused by many classes, and they always get mixed up. So if you have any doubt, ask me. Okay? Now, also, my writing stinks. So if you can't read it, ask me, and I'll tell you what that reads. Okay? So anytime you're ready, okay, and what you can do, you can be answering the first questions 1, 2, and 4. You can be doing your hometown. You can be writing down cities, or you can be looking up the things. So scatter it out. And this is a lab. You can work with a partner. You can work with one another. Help each other out. And be careful there, I'm afraid. Yeah. Okay. Okay. It's Tunis. Tunis is a city. Tunisia is a country. All right. Does anyone need this left up here any longer? Okay. Yeah. Okay. And again, I highly recommend write down the city before you put it back, and then put it back in the cup before you draw another city to make sure you're in the right one. And remember, you get a second city from either the Africa Cup, the Asia Cup, or the Europe Cup. You'll get a second city from 2 of those 3 cups. So you can get 10 cities. 1 from each cup, and a second city from 2 of the 3 Africa, Asia, or England. Europe. Ugh. Again, if you have any doubt that the city you drew out is in the right continent, ask me. I'll be glad to tell you. And just like I told Ishmael, my writing sort of stank. There is a city called Tunis in the country Tunisia. So he was thinking I had written poorly, but I had, but that was correct. All right, can I go on and shut down the Screencast-O-Matic and start loading it? Does anyone need this any longer? Okay. Imagine if there are questions, I won't